In this video, I want to give you guys the intuition of the how and also the why for L'Hopital's rule when we evaluate limit. Let's take a look at this example. We have the limit as x approaching 1 of ln x over x squared minus 1. Well, we should always plug in this number into all the x's and see what happens, right? When we do that, ln 1 is equal to 0. And then when we plug in 1 into here, 1 squared minus 1 is also equal to 0. Which we get in determinant form. But this is pretty good because we get to try use the L'Hopital's rule. So by L'Hopital's rule, we can say this limit is still the same limit as x approaching 1, but instead of comparing the original top and the original bottom, we are going to compare the derivative of the top and the derivative of the bottom. On the top, the derivative of ln x is 1 over x. On the bottom, the derivative of that is 2x. Now, guess what? We no longer have indeterminate form, because if you plug in 1 into here now, it's just 1 over 1, and if you plug in 1 into here, it's just 2 times 1. Of course, 1 on the top, 2 on the bottom, and we get a nice number, which is going to be our nice answer. And then we are done. As you can see, L'Hopital's rule works so magically, right? But why though? How exactly does this work? Let me give you guys the explanation for that. I'm just going to remind you guys that if we are talking about the derivative, of course we should know the definition of derivative. F prime of a, I'm going to write down this version, is the limit as x approaching a. There's also another version, right? H approaching 0, but we're talking about this version here. On the top, we get f of x minus f of a over x minus a, which is just the slope formula with the limit. That's all. When we look at this function, if I really want to talk about the derivative, we should have in this form. Notice when we have x approaching a, on the bottom we wanted to have x minus a, but I don't have x minus a. This is x squared minus a. Yeah, x squared minus 1. So not exactly the same. So what we can do is the following. Check this out. On the top, I'm going to divide it by x minus 1. So on the top we have ln x, and I'm going to divide that by x minus 1. On the bottom, we have the x squared minus 1. I'm going to divide that by x minus 1. And you don't have to worry, because when x is approaching 1, x is not exactly equal to 1, so we are not dividing by 0. Now if you look at this part, it does look like the definition of the derivative. But how about this though, because I only have ln x. Well, don't worry, because we can do the following. This is ln x. I can write it as ln x minus ln 1. Why? Because note that ln 1 is equal to 0. So I can purposely put it here, so that means you can see this is the function and this is f at that 1. The function at that x value 1. Now check this out. Here it's a limit law. I'm going to look at this. This is the limit of a quotient, which is going to be the quotient of the limit of the top and the limit of the bottom if the top and bottom, the limits both exist. So I'm going to look at it like the limit as x approaching 1. I pretty much put this right here, which is ln x minus ln 1 over x minus 1. And then over, put a limit for the bottom. Limit x approaching 1 of x squared minus 1, and then over x minus 1. Now, if you look at the top, this thing right here represents the derivative of some function, right? Well, it's going to be some function at the x value equal to 1. What's the function though? I'm just going to write that down, where our function is ln x, right? Just that. The top, this limit right here represents f prime of 1, where the function is just ln x. Now, For the bottom, it also represents the derivative of some function. Let me just write that down. It represents f, well, I used f already, so I'm going to use g prime of 1. But here, our function is what? Our function on the bottom is g, which is x squared. And now, if you look back to over there, that is exactly what we did. This top limit represents f prime of 1, where the function f is ln x. So of course, to get this, we will have to take the derivative of ln x, which is 1 over x, and then we put a 1 into the x. On the bottom, well, we have to differentiate x squared, and that's how we get the 2x, and then plug in 1, so we have the 2 on the bottom, and we get the 1/2. And I know, right here, technically we are differentiating x squared minus 1, but this is just a number, doesn't matter. So as you can see, this right here is how L'Hopital's rule works. It's really that you want to introduce new things without changing the value of the original limit, so that you can match the limit with the definition of the derivative. Right? Pretty cool, huh? And of course, I know there's another version where you have infinity over infinity. You also get to use L'Hopital's rule, but I just wanted to show you guys this right here, because this right here matches with this very, very nicely. You can think about how you will prove the infinity over infinity case. I will leave that to you, or maybe in the future I will do another video for you.